Welcome to section 3.2, differentiability. In this part 1, we will talk about where the derivative actually fails to exist. Those are usually just a few points, one usually on a graph, and we'd say that the function is differentiable at all other points on the graph of the function. The graph of a differentiable function, so what does it mean to be differentiable on an interval or everywhere? What that means is that its graph, we can draw a tangent line that's not a vertical tangent line at every single point in the domain or on the interval that we're talking about. If we can't draw a tangent line successfully that is not vertical, then it is not differentiable at that point. We're going to take a look at 4 types of non-differentiability. But first, I want to talk about the fact that all polynomials are differentiable. A polynomial just means like x squared is a polynomial, 4 is a polynomial, 3x to the 5th minus 2x to the 8th is a polynomial. Basically, there's no x in the denominator ever. There's a few other caveats with polynomials, but that's the main one. So I want to take a look at a graph of a common polynomial and talk about why it's differentiable on its domain, which is all real numbers. I decided to go with one that's maybe not as popular, but my idea is that it combines like popular functions that we know. We know x cubed, x squared, x. This is just a cubic trinomial here. And so polynomials have this kind of roller coaster shape unless they're linear, in which they're a line, or a constant, they're a horizontal line. But most polynomials look something like curvy like this. And basically, if you're curvy and smooth all the way through, you're differentiable all the way through. No matter where we go on this graph, the graph of this function, we can draw a tangent line that is not vertical. We could draw tangent lines anywhere on this graph. We could draw one here. We could draw one down here. Could draw one down here at this local minimum. It's horizontal. And we could draw those anywhere on the graph of this function. So all polynomials are differentiable. Let's take a look at when it's the case when a graph of a function is not smooth and curvy and points that make it not differentiable. Here we have a little graphic organizer of the 4 points of non-differentiability. This is kind of like my made-up word salad right here. I don't even know if non-differentiability is like a math term. It's not in your book anywhere, but we'll just say that it is. So there's 4 different situations in which we'd have a point or points on our graph of our function where we're not differentiable. The first one I'm going first here because we've talked about continuity. When a function is not continuous, that means it's not differentiable. And we do have 3 types of continuity. Remember, we had a jump discontinuity, we had a removable discontinuity with a hole, and we had an infinite discontinuity where there is a vertical tangent line. So when a function is not continuous at a point, here the function is not continuous at x equals a, we would also say that that function is not differentiable at x equals a. The next time, or the next scenario in which our function is not differentiable at a point would be when we have a corner. This is a common graph, it's the absolute value function, and we can see that it comes to a corner when x equals 0 down here at the origin. This is the parent function for absolute value. We could, doctor it up a little bit. It can move left, right, up, down, get more narrow, flip over, whatever. All absolute value functions are an example of they have one point that's not continuous. So this function here, the absolute value function, is continuous everywhere except when x equals 0 because there's a corner there. We'll talk a little bit about why that is as well. The third situation that we have where our function is not differentiable is what's called a cusp. And a cusp is very similar to a corner except that either both sides of it are like curvy or one side is curvy. It's not a very mathematical way to describe it, but it's a good visual way. So this is kind of a cool visual that has 2 cusps, 2 different types. We can see that this leftmost cusp when x is 0, it has a linear piece over here, and then it looks like a quadratic piece here. So it's curvy, and then straight here. This cusp has 2 curvy sections. So the function is not differentiable at these 2 points, at x equals 0 and like x equals maybe 1.8 or so. The last spot in which we would have a point on our graph that's not differentiable would be if we were to draw a vertical tangent. We see that this graph here, this is actually the graph of the cube root of x. If we were to draw a tangent line when x is 0, that tangent line would actually be vertical. So these are the 4 situations in which we would have a point on our function or on our graph of our function that is not differentiable. In all of these cases, all other points, all other x values on the graph of our function are differentiable. It's kind of like domain in a sense that we say x can be everything but 2 or something like that. We sort of define differentiability by picking the spot out where it's not differentiable and saying, hey, we're differentiable everywhere else. In this first example, we see we have kind of a strange piecewise function. I'll label it f of x. I always forget that part. We're going to talk about not only differentiability, but also continuity. Differentiability means we are continuous, that we can keep our pen or whatever on the function without lifting it or jumping or anything like that. But differentiability also means that not only it has to be continuous, it has to be smooth as well. So let's take a look at part A. We want to see at what points does our function appear to be differentiable. Well, we are going to just say it's differentiable everywhere except for the few spots that it's not. There's an infinite amount of points in between -8 and 7, looking like that's what our domain is. And as we look from left to right, we're good until we hit our first corner here at x is -6. So we're not differentiable at -6. There's our first issue. Then as we keep going from left to right, we have this discontinuity here, a jump discontinuity at -4. Therefore, we're not differentiable there. Then we keep moving from left to right on our function, and then we hit a cusp here when x is +4. And then our function stays nice until the end at x is 7. So we are differentiable on all points in our domain, which is from -8 to 7, and we'll say except these 3, except at -6, -4, and 4. Didn't mean to write that in such a strange way, but on all points from -8 to 7, except, boom, right here. We could have written this in a different way, but I feel like this is easier than writing all those separate intervals. All right, part B is asking us, where are we continuous but not differentiable? Well, we've already found where we're not differentiable at these 3 spots. So let's see if we're continuous at any of those. Are we continuous at x is -6 here? Can we go past it without lifting up our pen? Yes, we can. We're continuous here. Even though it's a corner, we're continuous. So we're continuous at x equals -6 rather. Then I want to look at the next spot where we're not differentiable, which is x equals -4. Are we continuous here? No, we have to have a jump. We cannot, we have to lift up our pen to get to the next part of the function. So this is a jump discontinuity. We're not continuous at x is -4. Let's check out the last point of where we're not differentiable at 4 over here. Are we continuous here when x is 4? Yes, we do not have to lift up our pen, in this case my pointer over here, so we are continuous at 4 even though we're not differentiable. So at corners and cusps, and even if there's sometimes a vertical tangent line, as long as we don't have to lift up our pen on the graph, we can still be continuous. Differentiability is a lot more finicky. Let's take a look at part C. Where are we neither continuous nor differentiable? Well, we saw that there was really just one main issue here, which was when x was -4. We're not continuous there. There's a jump discontinuity, nor are we differentiable because we're not continuous. So only at x equals -4. This video was pretty quick because this idea is not too crazy. In our next lesson, we will talk more about the relationship between continuity and differentiability, But for today, I really wanted us to just focus on a visual aspect, looking at the graph and visually seeing those points where we're not differentiable or where we're not continuous.